Hi everyone, thanks a lot for joining the talk. My name is Nikunj, and this is a talk on HPX and mostly for people who are beginning with concurrency and parallelism. I've taken the slides from a lot of other people as well, so this is not entirely my own presentation. I've taken inspiration and materials from my mentor Hartmut Kaiser and other members of HPX group. So John, Thomas, Giannis, and many other have contributed to the slides that I'm going to show. Um, so a brief introduction about myself. I'm a computer science undergrad from India. I'm still in my final year, and I'm a core member of the Stellar group. And I love playing with C++, as Ankur told. And I actively contribute to the open source project HPX. About the Stellar group, it's a research group led by Professor Hartmut Kaiser at LSU. And it's more of an international led group. So we've got collaborators across the globe from India, from Russia, from Germany, Argentina, Greece, and many other places as well. So it's more of an international research group, and we mainly focus on two projects. There's one HPX, which is a C++ standards library for concurrency and parallelism, and the one that I will be talking about in the presentation. And there's the other one called ParalleX, which is an asynchronous distributed array computing toolkit. It's mainly for working with machine learning and AI stuff. Today we'll be mostly focusing on HPX and also mostly on the basic features of HPX. So I'm not going to talk a lot about the distributed aspect of things or executors. So it's mostly based on basic concurrency. So if you're an expert in concurrency and parallelism, if you know what tasking is and you know how to write parallel codes, this talk is probably not for you. But if you're just a beginner at all of this and you really want to get into how things work, then I believe this talk should not only help you understand what HPX is, but should also be able to help you with writing C++ codes. Based on the presentation, I'll be talking mostly on the need for task-based initially. So why we need HPX or in general any task-based programming models. I will introduce you to futures. It's essentially the same thing as C++11 futures, but with more features. Then I'll take you to a tour of HPX and help you understand what HPX is and what sorts of features we have and what our main goal is. And then I'll talk obviously about the hello world in HPX because quite frankly, any talk will be just garbage, I'd say, without an explanation of hello world. Then we move on to futures in HPX and ways we do tasking in HPX. And then to consolidate everything, we'll talk about Quicksort algorithm. I picked up Quicksort because it's easy to trying to consolidate things in a single slide with respect to code. So we'll take Quicksort from a serial implementation to a parallel implementation to an asynchronous implementation. And we'll end with what next, as in the conclusion about HPX, what more does HPX offers, and if you want to go ahead and read up on more tutorials or talks on HPX, I'll have links there. So starting with the first thing, why do we need task-based models? So if you see the image that I have up here, this is how most of the parallel programs look based on OpenMP. All we have are these areas, these green areas. These are areas wherein the CPU is actually doing work. And between these green areas, you can see these white spaces. These white spaces are the places wherein the CPU idles. That is, CPU does not do any work. And most of the OpenMP program, or quite frankly, any of the standard fork joint parallelism-based program, work according to this way, wherein you have these sort of parallel sections wherein you do a lot of work, and then you have these idle sections called barriers due to barriers, and that's where the CPU idles. Now we'll talk about everything in detail about why this is bad and why we need tasking in this chapter. And if you have any questions, you can ask me right after the chapter ends so that I have spoken everything there is about that chapter, and then we can try to make things more interactive. And if you have any questions, I'll take that up and try to answer them for you. So the current day problems. We need to realize that we have problems with the current day implementations of parallel runtimes. Most of the codes that are written in today's age are based on MPI and OpenMP. And if you are a GPU programmer, then you have OpenACC, you have CUDA, and other such programming frameworks. And all of these have some sort of deficiencies. So let's talk one by one on what the deficiencies are. The first one is insufficient parallelism imposed by the programming model. So for example, if you take OpenMP, as I just said, OpenMP, the way things work is you have a for loop that you want to parallelize. You add in a pragma directive at the top of that for loop, and what it essentially does is it parallelizes that for loop, and in the end, once everything is done, there's an enforced barrier. You don't really need that barrier, but it's kind of enforced into the parallel programming model that OpenMP offers. Similarly, there's over-synchronization of more things than required by the algorithm. So for example, if you have MPI and you are running things on large cluster with, let's say, hundreds of nodes, what MPI does is it runs exactly the same code on all of those 100 nodes, and then you have these sort of communications between these remote nodes. So every time this lowest node will be acting as a lockstep between all of the other nodes, and therefore you're ending up hurting your performance by over synchronization. And that's a problem as well, because in the end you are having a performance bottleneck. Next is insufficient coordination between on-node and off-node parallelism. So the thing that we need to understand are all of these frameworks have been created independent of each other. So MPI is for distributed computing. So if you have, let's say, hundreds or thousands of nodes, how do you make things distributed and run in distributed setting? OpenMP is made for shared memory systems and NUMA systems, wherein you have a single node and you want to parallelize things basically in there. And sadly enough, there's not enough coordination between them. So they were never designed such that you can use OpenMP with MPI or MPI with OpenMP. Now you can obviously use it. People have been doing it for a long time, but it requires a lot of proficiency to have performance systems that have such coordinations between different frameworks. And finally, we have a lot of distinct programming models for different types of parallelism. And based on that, you see, you have various forms of MPI implementations available if you want to go distributed. But if you want to do things heterogeneously, you have OpenMP, you have OpenACC, you have CUDA, you have HIP, you have various other frameworks. And as I just alluded to in the previous point, that there's not sufficient coordination between them. So that's actually kind of hurting your performance in the end. And that's a major bottleneck, because in the end, what you end up having is a fork join based parallel model. So to understand what a fork join semantic is, let's look at this diagram to understand. So a serial program in C++ runs on a single thread. Let's call that a master thread. And if you have work sequentially on this thread, they are executed sequentially now. Now, let's say you have this simple program wherein you have for loops and you have parallel algorithms and whatnot in C++. If you want to parallelize it, it's very easy to do so in OpenMP. All you do is you add that pragma directive above that for loop, let's say a pragma parallel for, and then what happens is it converts that code such that there's this master thread, and when you have that for loop that you want to parallelize, it kind of parallelizes all of those tasks, and then once all of them have completed, it gets over here back to the master thread, wherein again instructions you execute sequentially, then it moves on again to a parallel section, executes things in parallel, then again it goes to a sequential setting. So overall, what happens is you end up parallelizing certain sections of the program, but you do not really parallelize the whole program. Furthermore, if we see how things work in a, let's say, fork join setting, is, let's say if you have an OpenMP for loop, and let's say it's not a uniform workload. What happens in the end is that you have all sorts of idle times, and these idle times are based off the slowest step of that for loop. So for example, in this case, this is a thread that takes the most amount of execution time, and therefore every single other thread, what happens is it ends up completing its work and then it idles. And this is also something that actually hurts your performance a lot. And the reason why I'm talking about these settings with master and worker threads and the point of idle times is because we are actually limited by Amdahl's law. So for those who do not know what Amdahl's law is, it essentially puts a bound on the strong scaling. So let's say if you have a program, a sequential program, and you end up parallelizing a certain section of that program. So what happens is you would expect a linear scaling over that, but it essentially does not happen because what happens in the end is that sequential program that you have, the sequential portion, even if it's, let's say, 50%, if it's not parallelized further, you actually, even though have parallel sections in your code, that sequential section will end up being the bottleneck of your code. So we really need to know that we need a lot of parallelism. For example, let's say in the graph, as I have on the right, if you have 50% parallel code, you cannot have more than 2 times the speed up. So that's actually not really good. If you only parallelize 50% of the code, you will not linearly scale to a large extent. Similarly, even if you have 95% of your code running in parallel, even then you cannot gain a speed of more than 20 times. And with the current day processors that we already have, you will understand that we already have cores that are more than 20 cores. So even the desktop machines with the latest Gen Ryzen processors, even they have 16 cores and 32 threads in total. So what's the point then if you cannot even linearly scale to that point, and you cannot get the speed up that you're really demanding? And that's really the current day scenario, the current day problem that we have. So in the end, what I would say is that not even the C++17 parallel algorithms that we have um, can actually make that go away, because in the end, even they are based on fork join parallelism. So all that happens is you have these execution policies attached to these C++17 parallel algorithms, and in the end, you're only parallelizing a certain section of the code. So in the end, you always get hurt parallelizing codes, and you will not gain the speedups that you actually are trying to demand and you actually expect from the system. So now that we've understood the issue with these fork join primitives, we need to come up with a solution. And the solution is actually very simple. We run things as a task now, and that's called the task-based system or task-based programming. Essentially, you break down all of your code into tasks. So in the end, what you end up having are tasks as shown on the right side. And these tasks can have a flow of execution. For example, the task 1 can initiate task 2, 3, and 4. And based on that, let's say these 3 and 4 can invoke a task 5. And this task 5 will have a dependency on these 3 and 4, and so on. So overall, what you end up having is a program that's composed of tasks now. So it's not essentially a single master thread that breaks down to a worker threads which does work and then get back through barriers and then go ahead to the master thread. But what we have now is we have tasks, and since we have tasks and we have this flow of execution, we can let the runtime extract as much or as little parallelism, as long as it again follows the user constraints. That is, it follows the execution order of these tasks, in the sense that 3, 4 is dependent on 1, so 1 should obviously be executed before 3 and 4. So based on this, we can have a scheduler that's essentially the runtime itself, and these scheduler will work on these constraints, and based on that, we will have tasks that coordinate between each other, and these will be scheduled and will be executed on cores. And since now we have a scheduler and it knows very well about the task itself, we can dynamically at runtime maximize the code throughput and minimize the wait times through scheduling. So in the end, what you end up right now is that, instead of having these sequential section that again goes into worker threads, you have these tasks running asynchronously, running all the time as long as you have enough tasks in that system. And that's what I'm going to come up with HPX again, is that if you have fine-grained tasks, that you can have millions of such tasks running asynchronously, and the runtime will make sure that your cores are always filled up with some form of time. So it won't idle, and the in the end you won't have a picture that looks similar to this. You will have less idle times, and you will have more work that is done by CPU. So something that's taking 120 seconds over here with, let's say, 40% of idle time with CPU might just take about 90 seconds or 100 seconds when you do things in a task-based manner. So also what task does is it hides the details of multi-threading. So if you work with threads in C++, you may have realized that there are a lot of things that you need to take care of. So you have to work with mutexes, you have to work with conditional variables and whatnot. And in the end, you're actually trying to implement and re-implement things yourself. You have to take care of all the whole synchronization things. You have to take care of everything yourself. So what happens with task-based systems is, since you're already doing things in terms of tasks, the runtime has the potential to handle synchronizations for you. So you no longer need to work with mutexes. You no longer need to work with conditional variables. And by the way, that comes with an asterisk, because if you have, let's say, concurrent data structures, then you will obviously have to work with those concurrent conditional variables and spin locks and whatnot. But in the general setting, if we have, let's say, a task-based programming model, we can let the runtime handle synchronizations that happens within tasks. So this way, the runtime will be able to extract as little as much as parallelism as I just told you in the second point. The next thing is, we do not have to create threads our own this time. So since we're working on tasks, we just need to create tasks. So we do not work with threads. And since, again, as I just said, if we do not create threads, there will be less locking, there will be less races, and there will be less waiting in the user code. So in the end, what you end up doing is you end up submitting everything to the tasking system itself. And this way, all of those synchronizations that you're ending up doing with threads, that's handled by the task-based runtimes. So that's a brief outlook on tasking systems. So if there's any questions based on that, let me take that right now. And if there's, yeah, go ahead.
Do you know about the C star framework?
Could you elaborate more on that one?
It's basically what you said. It's a task-based programming model. It defines its own future. It's a C++ like framework, and it does essentially what you said. Like it creates tasks, and you create future, and it the future has a .then method which you can use to chain tasks together, and it basically does what you said. Like it's the same thing.
Right. Unfortunately, I have not heard of it. But yeah, there are various task-based systems. So HPX is not the only one. There are multiple others. There's Legion, there's Tram++, um, there are separate ones in Boost as well. So it's not the only task-based system. But I will come on why HPX and why you should be using HPX in terms of when you want to do task-based programming.
Nishant, you can unmute yourself. You raised your hand. You can ask your question.
Okay, so let's go on to the next chapter, that's tasking through futures. So now that we've talked about tasks and what task-based programming is, we need to know how to do things, or how to create tasks. So the idea behind creating tasks can be as simple as doing things with futures. What is a future, you ask? A future is an object that represents a result which has not been calculated yet. So essentially, let's say if you had a threading system and you created more threads and did synchronization, what a future does for you is it extracts that part of the thread into a different locality, different thread, and in the end, it essentially takes care of the whole synchronization between these two tasks now. And what happens in the end that you lead up with is that you have transparent synchronization with producers. So let's say this is a thread A, and this is, oh no, let's say this is a thread A and this is a thread B. Now, if you invoke a future from this point on thread B, it just invokes things on a different thread, and it has and post its execution, it sets the value, it sets the result, which can then be later used in the thread B by using the get function. And that's how simple it is to create tasks. And the major advantage of creating tasks is that it hides the notion of dealing with threads. And that's what I told in the previous slide with tasking system as well. So you do not need to explicitly synchronize from the user's end. So you don't have to work with mutexes or semaphores or conditional variables and not and plenty of other things. And it essentially makes asynchrony a lot more manageable now. And finally, we can easily compose several asynchronous tasks by adding continuation. So as a person just told me about the task space with adding continuations, you can do so with task space as well. And that's how we have such a directed acyclic graph over here, wherein you begin with a task, you impose more tasks, then you can add continuations, you can have dependencies and whatnot, and in the end, the runtime will execute things such that everything's work fine. Let's take a simple example on future, and I really like to take this example from the Hitchhiker's Guide to the Galaxy, wherein we create a machine, let's call that deep thought, and all we're looking for is the answer to the question from of all universe. So, and we know the answer is 42 because we've read the book. We know that answer, but we do not have that 7.5 million years to compute that universal answer. So what do we do then? As I just told you with respect to futures, is you can create futures and you can have asynchrony involved because it will run on a different thread, and that's exactly what happens over here. You have a future, and we're saying that you will get the answer. You won't get it right now, but you will get it sometime 7.5 million years after. And so what you do is you invoke a future. You tell it to run that computation for those 7.5 million years. And then once that time gets over, you ask that machine to ask the kernel to give you the answer back. That is the using the .get function, as I just said over here. So thread A sets the value and thread B gets it. And that's the whole idea of futures. And yeah, so before we begin with HPX, I really want to make sure that you understand what I've been telling you right now, because all of this will come into picture now with HPX. So if there's anything you want to ask, then it's probably the right time to do so, because otherwise, yeah, you'll lose very soon with what I'm saying. Okay, so let's move to HPX.
HPX can you please tell a little more about future, like how it works?
So the way futures work underneath is you can imagine it to be invoked on a new thread. I'm not talking about C++ implementation, so I won't get into that, for example, but from an overview point of things, you can assume that to be run on a separate thread. And these two threads share a shared memory state. So what happens is one of the threads writes the value to that shared state, and the other thread gets the value from that shared state. And once the future gets the value from that shared state, it destroys the shared state, and you progress on with your computation. I hope that answers your question.
Yes, thank you.
Okay, so moving on to HPX. HPX is a task-based runtime system, and it's a general-purpose parallel runtime for applications of any scale. So you can run HPX on Raspberry Pis on 2 cores. You can run HPX on your personal computer or desktop computer, or if you want to, you can run it on clusters, and that's what we do. We are a high performance library, so we want to run things on supercomputers and want to scale things on supercomputers. So performance is the key essence to HPX in the end. Next is that we are standards conforming. So each of the APIs within the standard C++, we have them re-implemented in HPX. We do not re-implement things because we're a fan of re-implementing or like doing redundant stuff. We do so because we have a lightweight threading system that we make use of, and since we have our own threading subsystem, we will require to re-implement things like threads. We will have to re-implement things like mutexes and futures and whatnot. So that's why we re-implement things from the standards APIs. But the key point is we're still standards conforming. So if you have a standards conforming code, all you need to do is you need to change the namespace from stud : to HPX : and things will compile for you and things will run for you as well. So it's standards conforming, and it makes it easier to program. So, the reason why we made it standards conforming is because, again, large scale application, high performance computing applications have millions of lines of code, and you do not really want to code things again and again. So if you have APIs that was already standards conforming, all you need to do is you need to do a search and replace, and all of a sudden you have an HPX code, and that will run much faster than your standard C++ code. Also, the second point is that we need to support distributed and heterogeneous computing. So things like CUDA and GPU support and distributed computing, you cannot do so with the standards API. So for example, if you know about standards function or the bind function within the standards, you cannot really you cannot bind them to a remote locality. So let's say if you're on one locale and there's another remote locality on that same cluster, and if you want to invoke things on that locality, you cannot do so using the standard bind functions that we have in the standards API. So to support all of such applications, we have our own re-implementation of a lot of standards API. But as I just said, all you need to do is you need to do a search and replace. Now, the advantage of having our own threading subsystem, a lightweight threading subsystem, is that we allow fully asynchronous code, and you can use millions and millions of threads. When I say millions of threads, what I really mean is that you have millions of tasks that underneath will be invoked on threads. So you can have as many tasks as you want, and we actually want you to do you actually want you to write fine-grained tasks in the end. And the next thing is we have similar syntax and semantics for local and remote operations. So things like HPX async, you can use those for invoking kernels on the same locality, and you can do so for invoking things on the on another locality. So we have a very similar syntax and semantic for both local only and remote operations. Next is that HPX makes concurrency manageable with data flow and future-based synchronization. So we learned what futures are. HPX futures are much more powerful than what we just saw in the previous slide, and I will tell you what sort of features those futures have. And data flow is another such construct. It's another basic primitive in HPX that you should be using, and it's basically used to allow dependency management with tasks. And again, I have a slide later down, but as of now, you can assume that a data flow takes in a bunch of futures, and once all of those futures have executed and are ready to return the result, you invoke a kernel that is given to the data flow, and that is how we essentially manage tasking with respect to data dependencies or task dependencies. Finally, HPX is also an open source project under the Boost license, so you can essentially do anything you want with it. We would very much appreciate if you give us a feedback when you use HPX so that we can work on it and further improve upon it. But even if you don't do so, we're glad you're using HPX. Now, as I just said, we have a lot of replacements APIs in C++ from the C++ standards in HPX, and we try to keep it as possible to the current C++ standards, and we also extend those to the proposals that are in C++. So for example, what we have in C++11, the stored future, that is not as powerful as the one in HPX, because we support the concurrency TS technical specification, and similarly our async functions can support executors. That's again another proposal, and should be, I believe, C++23 should have executors in it. But yeah, so we support a lot of other things as well. So async also support doing distributed computing, supports executors and whatnot. So in the end, what we end up having is C++ APIs, C++ standards conforming APIs that not only provides you the features that C++ currently have, but much more than that. And just for reference, for example, things like threads, mutexes, and futures, and async, these were re-implemented because we have our own threading subsystem. It's a very lightweight subsystem because the C++ uses pthreads for the implementation, or on Windows it uses the Windows threading system, and those have really high overheads of creation and deletion. So we needed a way to get around it, so we created our own user level threads, and based on that we have our own threading subsystem, our own thread pools, and our own implementation of threads, mutexes, futures, and so on. Things like bind and function, we have those re-implemented because we want to support distributed operation. So for example, if you want to bind a function that you want to invoke on another locality, you cannot do so because C++ APIs are not serializable. If you don't know what serializable is, let me just explain you in a couple of sentences. So the thing is, let's say if you compile things and you're executing things on multiple different localities, a function, let's say if it has an address A on one of the localities, it will not have the same address A on the other locality as well. And that has to do a lot with the address-based randomization that happens in the OS. So we need to keep that in mind. So we re-implement things from the standard so that we support the serialization, wherein even if you serialize a function from one of the localities, it automatically detects the address on the next locality. Similarly, we need to re-implement tuples because we need to support GPUs. We re-implement CR because since you have HPX codes running on a lot of localities, you may want to do get the output on one of the consoles and not on the other localities and so on. Similarly, we support C++ parallel algorithms, most of them, and we also support ranges and parallelism on ranges as well. So yeah, there's a lot of things that are within the HPX library, and that's what makes it a really good place to start with concurrency and parallelism in your code, and that's why I really recommend this library. Next up, let's talk a bit about the HPX architecture. So HPX allows wait-free asynchronous parallel programming, and I won't go a lot into depth with the architecture. So let me give you a brief overview. So we have a threading subsystem, as I just said. We have implementation of lightweight threads. Based on that, we have these local control objects that we use for synchronizations. So these objects are responsible for synchronizing between tasks and even distributed tasks. Similarly, we have the network layer, mostly for the distributed stuff, for sending messages from one place to the other and so on. And similarly, we have the active global address space, which is essentially a key value hash map, which takes care of knowing the addresses of various functions and whatnot in the HPX. Yeah, so I kind of understand that whatever I've been telling you has been a bit more on the theoretical side. So I'm glad you bear with me, and let's start with the hello world. If you have any questions right before it, let's take that, and if not, we can continue towards code, and let's try to understand how HPX code works.
Hello, I wanted to ask a question, Nikunj.
Yeah.
Can you go to the previous slide just before this one?
Sure.
So, how exactly, you say that these are the HPX replacement for the standard C++, right? Like for
Yes.
instance, STDC out is replaced by HPX out. So how exactly is, like, I mean, I am not a professional in C++, but as far as I have used C out, I don't know how will someone. I cannot imagine how someone will apply parallelism in C out, right?
Ah,
For a
okay.
for loop, I can imagine, but for a C out, I cannot. So, like, can you explain like how in C out and for each, like how exactly, what exactly has HPX done differently as compared to the standard C++ that exists?
So features like cout, bind, and functions, they are not exactly functions based on parallelism. They're not trying to parallelize anything. The reason we have HPX cout, for example, is that it keeps its own buffer. So if you want to buffer in things with respect to cout will not might not work when you have a distributed application. So just to cater to those situations, we have re-implementations of those. We are not parallelizing it underneath. We are not parallelizing any of a bind or function either. They're mostly replacements because we need to make sure that they support the features that we want to support.
Okay.
Right. So anyway, let's get
Nikunj,
into
I had a question. Sorry.
yeah.
You have an HPX async. The STD async always instantiates a new thread. I guess in your case, it is a task.
Right. So the async, if you do not provide a launch policy, if I remember correctly, does not invoke a new thread. It just uses the same thread to work with. In async with HPX, we invoke a new task. Yes, we invoke a new thread, an HPX thread this time around, and we invoke it on those. I will come back to async and what sorts of launch policies it supports and what you should be knowing about async in the future slides. But as of now, yes, when you do async, it invokes a new task and that task runs on a new HPX thread.
And a small question. You talked about a function moving from one locality to the other.
Right.
And so you have to compile with that function, or is it something like JIT?
Yes, so it's since it's a library, we do not have our own tool chains. The way we do it is special template metaprogramming techniques. That's a bit more advanced, but to simplify things, let me try to simplify it in a way that you can understand. So the way it works is we have a template, and using macros, we first convert a function into what we call an action. An action is a serializable entity, and it's essentially a structure because when you have structures, you can make it callable by having operators, and you can make objects of that structure as well. So essentially, what we do is we have a template specialization for such scenarios wherein you take that structure and you take that address. And now what we do is we kind of rely on the linker at runtime to do things for it for the second for the address of the for the address as a parameter to the second template function. But yeah, that's how we do it. We do not really send in, since again as functions have function pointers and function pointers are not serializable. We need to come up with a way that's serializable, and that is through objects. Objects in C++ are serializable. So we create structures, and based on those structures, we create actions based on it. Now this is a bit more advanced stuff, so I'm not sure if I'm coming out very clear, but
Yeah, good for me. Thank
okay,
you.
sounds good. So anyway, hello world. The hello world in HPX is actually very simple. All you do is you initialize an HPX, the runtime system, and the default entry point for the runtime is HPX main. And within the HPX main, you can use all sorts of HPX facilities. You can use futures for tasking. You can use other HPX facilities I've been telling you, for example, vectors, CL, and whatnot. And yeah, that's how simple it is. What you need to understand that you need to initialize the runtime and you need to finalize it. And we do so because when you initialize the runtime, you essentially initialize the whole thread pools and the whole threading architecture, the AGAS subsystem, the networking layer, and everything. And similarly, when you do finalize, you actually destroying all of those so that you can get back to the starting point of your application. So yeah, that's all very simple. But let's say if you want to start very simply and you only have to use basic HPX features, we support another thing. It's called the HPX main header. So if you realize previous slide, we have the HPX init header. What it does, it allows you to initialize through the HPX init function. And if you have HPX main, we do things for you. We make use of special linker magic underneath the hood. Again, that's quite an advanced stuff, but I can talk about it at length because I was the one who implemented it in HPX. So essentially, we use some sort of linker flags and linker and compiler optimizations and some sort of flags to do magic and initialize the whole application and finalize things for you. And if you're a fan, if you don't have to do a lot of tasking, or if you do not want to work around with a lot of more complex things, for example, so HPX init allows you to do much more than this. It allows you to add terminal command line options. It allows you to tell the runtime how to schedule threads, or if your system is a NUMA system or not, and a lot other features that we provide. But if you're not using those, if you're just if you're working on a personal computer and you want parallelism and concurrency in your code, all you need to do is you need to just include that HPX main file, and we will do all sorts of magics for you. So you can simply go ahead and use those features within. So before we move on more complex stuff, let's try to understand what features and what features are provided in HPX. So features as of C++11 provides you with a few functions. The get function that you use for getting the result, valid to check if there is a shared state. As I just said previously, answering a question, you can think of an async as a task running a thread and having a shared state. So valid simply checks if you have a shared state or not. If you do not have a shared state, then you cannot do a lot of other stuff like .get. Waits for the results to be available. Wait for is wait for a certain time or duration. So if the result comes in that time or duration, you get the result ready. Otherwise, you get a timeout status flag. Similarly, wait until is another such thing wherein you give a time step. This time, not a time duration. So you give a time point to the wait until point, and if the result does not become ready by that time, then things are changed. Now, features in HPX provide additional things from the concurrency technical specification in C++. So it allows you to attach continuation using the then method, and it also allows you to check if the result is ready using the isReady function. And generating features is actually very simple. All you need to do is you have HPX async that takes in a function and a bunch of arguments. You can also provide launch policies as the first argument, but by default, everything launches on a new HPX thread. And as I just said, HPX threads are very lightweight in nature, so you don't really need to worry about creating more threads over here. The only policy that's worth noting is HPX not sync, HPX launch sync, my bad. So HPX launch sync ensures that HPX uses the current thread of execution to run that function that gets the arguments. Similarly, other ways of generating features is you can have parallel algorithms that takes parallel or sequential task policies. So we will come on the execution task policies in the future slides. And then we have concurrency APIs as well, concurrency technical specification APIs that generate features as well. So concurrency technical specification adds in a few more functions in the C++ standards. They have not been standardized, and I certainly don't hope that I have a feeling that they won't get standardized anytime in the future as well. But yes, so concurrency TS provides you with more APIs, and we have re-implementations of those. Not re-implementation exactly, implementations of those. So one of them is when all. So it essentially returns a future that becomes ready when all of the futures that are passed to that function becomes ready. Similarly, we have when any, which returns a future that becomes ready when at least one given future is ready. And similarly, we have finally make ready future, which produces an instant future with the value that you pass to it. And something that's native to HPX is HPX data flow, which is an optimized equivalent of doing a when all and then adding a continuation to it. Essentially, it does one copy, it avoids one copy in the end. So that's why we call it optimized equivalent, and we tend to use it more often wherever we can. And also it's more readable when it compares to when all with a bunch of arguments and adding a continuation there. Similarly, we have also an implementation of wait all, which waits until all futures are ready. So it's again a blocking call over there. And as for example, let's consider more examples now. Let's say you have a vector of futures, results future, let's say, and you create new tasks on that. You push back tasks to that vector of futures, and you want to wait once all of those tasks are ready. What do? You use a wait all API and pass that vector to that wait all, and things will work for you. It will wait until all of those results are ready. Once they are ready, it will stop blocking and it will execute the next instruction. Now, do note that all of these examples are merely examples, and you may or may not use it in the same way or the same scenario. For example, if you have a situation wherein you only want to execute one single algorithm, you may want to switch to a for each and then give that for each this algorithm to run. So yeah, things may be different, but as an example for wait all, this is something very basic for you to understand. Similarly, data flow. Let's say this time around, you want to have a continuation once all of these futures are ready. What do now? We have this time data flow. We launch it synchronously because we only want to, let's say, see out one single statement, and that's not a lot of work in terms of task grain size. So we tend to do it synchronously so that we don't end up with more thread contention. So we launch it synchronously, and we simply return all of those results that we received. And that's how simple a data flow API looks like. And over here, you may realize that we are moving the results, and that's because data flow takes in an R value reference. So if you want an R value reference, you need to move your results, or move the vector to the data flow. So similarly, all of these cases may or may not be asynchronous. And we really want you to write asynchronous code, because when you have asynchronous code, you have way many tasks, and the runtime can then schedule tasks and make sure that your cores are always not idling, always doing some form of work. So a basic example for serial versus asynchronous is as follows. You have, let's say, a make string function which goes on and calls some algorithm which returns a result. Meanwhile, you do some other work as well, and once everything is done, what you do is you send the result back as a string. The way you can do things asynchronously over here is by introducing first off a future for the some algorithm. And what it essentially does is, let's say if this is a complex algorithm, you run that complex algorithm, all of a sudden it runs as a task, and since it's running asynchronously, there's some other work also run in parallel while running the complex algorithm. And once everything is done, we can add a continuation over here using the then primitive. Again, we use launch because all we're doing is we're just converting it to string, which is again not a lot of brain size for a thread. So again, what we do is we take a future. Since again we take a future as an R value reference, we have an optimization. We can move the result, and finally we will have a string. And since this will return a future, this function itself will no longer be blocking anymore. So whenever you call this function, it will run as a task, and essentially it will not block your code, and will allow the runtime to parallelize things accordingly. And when you need the result for this task, then you can simply call the get function, or if you want to attach a continuation to this function, then you can do so as well. And again, in the end, all you're doing is with asynchrony, you have cores that do a lot more work than simply blocking. So parallel algorithms. Parallel algorithms with C++ 17, you know that We have support for parallel algorithms in C++. That's done using the execution policies that are added as an additional parameter, the first parameter. So in C++, there are various parallel execution policies supported. The key one, the key-worthy noting one, is PAR, which is the parallel execution policy, and the SEC, which is a sequential execution policy. So if you do not provide any execution policy, the default policy that is used is the sequential execution policy, in which case it's a blocking and it's actually running as a sequential operation. It's not parallelized in any way. In HPX, we provide you with two more policies, namely the PAR task and the SEC task, which is essentially a parallel task execution policy and sequential task execution policy. With task execution policy, what we're doing is we're converting these algorithms to futurized algorithms, to asynchronous algorithms, and these algorithms will then no longer be blocking in nature. For example, if you have the parallel fill on a vector that fills in a value inside a vector parallelly, if you have, let's say, an execution par, this is a blocking operation in HPX. This is a blocking operation, and what essentially happens in the end is that it is parallelized, but it is very much similar to C++17 algorithm. But if you have, let's say, a par of task, this will be executed as a task now, so this won't be blocking anymore, and you can and instructions after this this operation will execute asynchronously. The other ones that C++17 has are data par and par unsec and par unsec. These are pretty, again, advanced stuff. The easiest way to understand them is they are just like par is thread safe. No, not thread safe. So just like parsec is thread safe, unsec, and these par unsec operations are vectorized safe. So what happens in the end is that you cannot use locks, you cannot use atomics, you cannot use anything that cannot be vectorized in a way. But again, these are advanced stuff, and let's not talk about that right now. The key important stuff, the key important execution policies are the par sec and the par task and sec task execution policies. And we also use executors when using execution policies. So we can discuss on executors post this talk, but as of now, based on C++17, let's talk more on the execution policies. And again, we have a lot more parallel algorithms implemented. So this is a set of algorithms. We have others as well now with C++20, and we have support for, again, for task-based execution policy, for the parallel execution, and also for the parallel task execution policies with them. So let's put it all together in an example for Quicksort, for going from serial to asynchronous. But before we do so, I just want to make sure that you kind of understood what we're talking here, and you understood the primitive that I've explained. So any questions?
Yes, Nikunj, it's clear.
Okay, great. So let's put all of this together in a Quicksort example. I again chose Quicksort because it easily fits into one single slide with the C++ implementation. So it makes it easier for me to explain how to go from serial to parallel to asynchronous and creating algorithms that way, algorithms that are both performant and does not block as well. So here's the simplest example. You take in a random iterator, and this Quicksort takes in the first and last random iterator, just like all other standard C++ algorithms. I took random iterator again because I wanted to make things smaller in terms of code size, but you can do so with a forward iterator or a bidirectional iterator as well. But for the time being, let's consider random iterator. So what we do, we check the size that we have of the container. And if that size is greater than 1, we need to find a pivot. So yeah, just before explaining this, I hope everyone know what Quicksort algorithm is, right? Okay. Go ahead.
I was going to say that you can give a small recap if you want.
So a Quicksort algorithm, essentially, what it's a divide and conquer algorithm wherein you have a pivot, and based on that pivot, you divide the array or the container itself into 2 parts, and then you recursively call quicksort on those parts. And the partition function and the pivot actually works in a way that you will have this element pivot, and all of the elements right towards that pivot will be greater than the value of that pivot, and similarly, the elements left of that pivot point will have value less than the pivot. So in the end, what you end up with is 2 subarrays, such that all of the elements in the right subarray or the right container, right side of the container, will have values greater than the pivot, and similarly for the left side will have value less than the pivot. Fortunately, C++ also has an algorithm for partition, so that actually makes my code even smaller and makes my time consumption low. So essentially what we do is we have partition, and we use the most basic form of quicksort, wherein we simply pick the pivot as the midpoint of the container. So we simply pass on the first and the last iterator, and the pivot this time around would be the middle element. Now, as you would have seen, I'm using a notation that is only that can only be used for random access iterator for random access iterator, and that's the reason why I'm using a random access iterator over the top over here. So essentially, what we do is we see if the value received is less than the pivot or not. If the value received is less than the pivot, it is sent to the left of the pivot. If it's more than that, it's sent to the it keeps itself to the right of the pivot point. And in the end, again, we simply call quicksort on the 2 subarrays or the 2 subcontainers within that container, and that's the whole algorithm itself. And it's a very neat algorithm. That's how C++ implements things within the STL library as well. And yeah, that's the quicksort algorithm if done serially. So how do we go from serial to parallel? We have seen C++ 17 parallel algorithms, and from there we know that you can make things parallel if we have the execution policy par in there. So if you want to do things parallelly, first thing is that you will use the par execution policy. And the next thing is, since we need to ensure that the grain size of the task that we're running, not exactly the task this time, the current the implementation underneath that we're trying to parallelize, that should have sufficient grain size so that when we parallelize, we do not see contentions coming out from threads. So we have a certain threshold overhead. I do not define a threshold, but it could be defined anywhere in the program or in the library that you want. So based on that threshold, if your size is greater than that threshold, we go ahead and we recursively call quicksort this time. But the pivot, finding the pivot has been parallelized to some extent. And similarly, if the size is less than that threshold, as long as that size is 1, what we could do is we could call sort on that part of the container, the subcontainer, and we can run things sequentially to ensure that there's no thread contention. And that's how simple it is to go from serial to parallel in quicksort. But as you may have noticed, it can still be it can still be more optimized in the sense that things are still blocking at this point of pivot. So let's say if you have a subcontainer that has a size less than the subcontainer on, let's say, the one below the quicksort one, you're essentially creating more work, and you're actually you are keeping the CPU idle at points, essentially. So it can be optimized even further, and the way we do is through asynchrony. And what we need to do now, essentially, is we need to make this a partition a task. So when we make it a task, then we get a future out of it. We get a future of random iterator. Now, again, we do not know the value of that future currently. So what we do is we attach a continuation to that future. And within the continuation, we get that pivot point, and simply we call the quicksort algorithm based on that pivot, and then we call a when all on that. What a when all does, again, as I just explained in the previous slides, is it waits, it gives you a result of, it gives you a future back that gets ready when the futures that are provided to that function gets ready. So this when all, this future that is returned from when all gets ready once the quicksort that is being provided to this when all gets ready. And similarly, if we have a size that is less than threshold, we again go to do things sequentially. And since we want to provide a future as a result, we simply return a make ready future. So that's how you can use all of those properties and create asynchronous code, asynchronous algorithms. And it's just a starting point. You can create way more algorithms. You can create way more tasks. And the best part about it is everything is a task right now. So the scheduler has all sorts of liberty to do things the way it wants to do, and it will ensure that your cores are not idling. And that's the whole key idea behind having a task-based runtime system. As long as you can define work in the form of tasks, you will have performance that will either compete with those of fork join parallel models, or it will outperform those in situations wherein you have imbalance between tasks. So yeah, that's like the basic overview of how you can use HPX APIs. Now again, what I've showed here is a very basic examples and basic APIs within HPX. You can do a lot more with HPX, and I'll come to that in the next chapter. But just to make sure, did you understand how we went from serial to parallel to asynchronous code? Or if you have any questions, you can go ahead and ask right now. Okay, great. So what's next? HPX has a lot more to offer than what we've seen in the slides. For example, there's executors. Executors, if you don't know what executors are, it's sort of an it's an abstraction over an execution resource, and provides you with sort of a functions, a genetic function execute, which you can provide kernels to, and that function will ensure that it gets run on that execution resource. Our executors are fairly outdated at this point. It's based on an extension of the P0443 proposal, revision 4. But we do have prototypes for senders and receivers within the implementation right now. Our futures are not derived from senders and receivers. They're still derived from the older executors. But yes, we do provide prototypes for that. Other than that, we have not touched upon the data-based parallelism and allocators. So HPX does provide you with NUMA architecture. So if you want to have NUMA-aware codes, that is having multiple sockets in a system in a single node, that we support. We support distributed systems. Again, we did not talk much about distributed system, if at all. And therefore, we also have heterogeneous computing with GPUs. So we support CUDA, we support HIP, and we also have integration with the Cocos runtime. I'm not sure if you've heard Cocos, but Cocos is another runtime that is mainly focused on heterogeneous architectures. So doing things on CPUs, GPUs, and working on different sorts of memory hierarchies. So yeah, we support all of that. We support distributed computing. Again, as I told, we have serializable entities. We call them actions. We have components if you want to share states between different localities as well. And we, based on C++17 execution policies, we also have distributed execution policies for distributed computing. We did not talk about communication between tasks. All we did was talking about tasks and how you can get results from one task to the other, and how you can have dependencies overall. But tasks can communicate as well. We have channels and local control synchronizations that help you do that. And again, we have C++20 ranges implementation as well. And we're the only library I know of that have parallel algorithms on ranges. And again, this is just a very short description of what we have. There's a lot more there is. And so if you want to dive deep into HPX, we have documentations available. If you want to have, talk to us, we can come on IRC on Stellar that's available on IRC Freenode, and you can talk anything you want with us, and we'll be more than glad to help you with parallelizing your code. If you have doubts, you don't want to come to IRC, you can also mail us to HPX users group. And if you want to contribute to HPX, we look very much forward to your contributions. And finally, if you want to go and take a advanced overview of what HPX can do, there are various talks by Hartmut Kaiser, my mentor, and yeah, my friend Yanis gave a talk this year, and I also gave a talk on executors this year at C++ Now. But there are plenty of talks to look for if you want to if you're not understanding the code base or you do not understand how to use HPX. There are HPX tutorials available, and there are examples as well available. Now I understand that this talk was fairly limited to a certain section of HPX, but I really wanted to emphasize on only some of the aspects of HPX so that you can understand and use them even with C++ or standard C++. And yeah, that's about it for my talk. Thanks a lot for being present. And yeah, if there's any other questions, I will be very much willing to take those up as well.
Yeah, hi Nikunj.
Hi.
Yeah, so could you please talk a little bit about the work stealing constructs in HPX?
Yes, so
it's specific to my use case actually.
Okay, so yes, so since I told you that we have schedulers that actually schedules things and threads on the runtime. So essentially, what happens is that when you initialize the HPX runtime, we have OS level threads that get attached to all of the cores on initialization, and all of these threads have their own scheduling system and work queues. And what happens in the end is we have these queues and these schedulers, and these kind of communicate between each other. So it allows you to actually do work stealing as well, and that can be seen easily with allocators and that we have provided in HPX. So for example, if you have a dual socket system, you want to only allocate things on one of the data, and you want to only execute threads on that socket. You can do so, and again, we do load balancing through work stealing underneath the runtime. And the best part again is that since everything is taken care by the scheduler, you don't really have to worry about all sorts of work stealing and the synchronization that's happening within the threads or the tasks. We do it for you.
Yeah, thank you.
You talked about heterogeneous computing using GPUs. GPUs, as far as I know, almost every library like Rockham, HIP, CUDA, they come with their own compilers, and those are Clang based. And like HPX is a library. Like, how do you do it?
Good question. So again, if you want to do GPU heterogeneous programming, you can do so by using CUDA compiler. You can do so by HIP compiler. And if you want to do through Clang supports GPU programming as well through CUDA and other interfaces. So you can do so. The way we have implementations for GPU and in general heterogeneous computing is that we launch a new thread, an HPX thread, and we give it the GPU kernel that we want to launch. And we have these sorts of state analysis that we do on these kernels. So when the GPU execution gets completed, it changes the state, and we return the future corresponding to that state, and you can call get on that to have these sorts of asynchronous tasking over there as well. So in essence, I mean, you will require a CUDA compiler to compile if you want to do heterogeneous programming with HPX. Or
Yeah,
you need to have
exactly
a compiler that supports those GPUs. Right.
Yeah. Thank you.
Nikunj?
Hey.
Yeah, Nikunj, can you hear me?
Yes, I can.
Yeah. What is the interface that HPX has with the OS? Is it like anything with the POSIX kind of standard, or how do you interface with the OS on creating processes and interface, exchanging messages between them?
I did not get the word that you're using. Could you repeat that?
Yeah, portable operating system interface, POSIX.
Ah, you mean POSIX? Yeah, yes. So the things that we have implemented in HPX is such that these OS level threads, they use POSIX threads. So for example, in Linux we use pthreads. In Windows we use the Windows OS threading subsystem, and in macOS we use macOS's threading subsystem. But they are very much limited to just initialization of those threads. Again, since I told you they are very much overhead. They have a lot of overheads of creation and destruction. So that's the only thing that we create at the initialization, and that's the only thing that we destroy at finalization. So to answer your question, you can actually have pthreads in HPX. We do not recommend you to do so because our threading subsystem is different to the one that POSIX implements, and you can end up getting race conditions and deadlocks and whatnot in your code if you try to intermingle these situations. So if you want to have HPX with POSIX subsystem, you have, let's say, an application that is based on POSIX, and you want to add HPX-based parallelization to it, you can still do so. The way we support it is through the start-stop mechanism within HPX. Within the Hello World example, I did not talk about it because that's, again, something that I consider a bit advanced. That's mainly used for our MPI-based applications. If you want to use HPX with those. So if you want to use with POSIX, all you could do is you can have that start-stop mechanism within HPX. You could use those, and within those single POSIX threads, as long as those POSIX threads do not sort of have these synchronizations within each other, or you will have a code that does not have any race conditions. It will not deadlock either. I hope that answers your question.
Yeah, thanks. Thank you.
Yeah, hi Nikunj. I had one more question. Does HPX offer any kind of SIMD wrappers for vectorized code?
Good question. I did not talk about the data for portions of things simply because it's vectorization and SIMD and stuff. So yeah, usually it kind of stresses people out. So we have those policies inbuilt. We use the VC library, which is which is a library for SIMD intrinsics, if you know about it.
Yeah, Agnerd Fogg's,
Yeah, and adding SIMD to your code is something orthogonal to doing task-based systems. So you can easily add SIMD operations to HPX as you want, use intrinsics and whatnot, and things will just work for you. And to answer that as well, I used SIMD intrinsics last year to write an application that we published in a conference. So you can very much do so in HPX as well. It very much supports it.
So the runtime basically detects your platform and architecture and those things, right?
Yes. So we support a lot of architecture. So as long, again, it's a library. You should remember that it's a library and it's not a language. So anything that C++ supports, anything that the architecture supports, you will be able to do things in HPX.
Got it.
So it's very much limited to the
I'll definitely look into it. Yeah.
Okay. Nice.
Quick question: which version of C++ is HPX using? 11?
So now we are currently have C++ 14 as a default compile time options. You could do C++ 17 as well. C++ 20 unfortunately is not very well supported within compilers at the moment, so we do not have ports of C++ 20 in HPX yet.
I have one last question.
Yes, no,
Yeah. So yeah, Nikunj, thank you for your time. Just one last question is that does HPX offer pragma directives so that we can quickly change existing code? Like I work on a code base that some of that has its own OpenMP directives, and the other part we have our own in-house scheduler that we work with. So
right.
Yeah.
So here's the quick point. HPX and OpenMP does not go very well together. We realize that simply because OpenMP again has its own threading subsystem built into the compiler itself. So to circumvent that issue, we created another framework called HPXMP. So what you may want to be looking at is HPX MP. All you need to do is you need to change those parallel loops. If you have, let's say, implementation in OpenMP, all you need to do is you need to change those into HPX MP pragma directives, and your code will run on HPX threads.
Okay. Yeah. Thank you so much. Yeah.